Yeah, so I'm going to talk about this online tool called QC Simplify that I've been working on. And yeah, first of all, so the idea of it is that it is a circuit builder, but it's a little bit different from the circuit builders that you might be used to. So as usual, there's a bunch of wires, and each of the wires represents what's happening to one qubit over time, going from left to right. And then we have a selection of gates, where each of these gates is something that you're applying to the qubit. So the X gate, for example, that's just like the classical NOT gate where it flips 0 to 1. But there's something a little bit weird about this circuit builder that you might notice, that there's no input or output. There's just wires and gates. And that's actually intentional, because the idea of this website is to try to help people gain an intuition for how the gates specifically interact with each other, and also how you can simplify a circuit. So for example, if you have an X gate or a NOT gate, and if you have a second one next to it, then two NOT gates together cancel out. So as soon as I let go of the mouse, these two disappear because two X gates cancel out. And similarly, two Z gates cancel out, two Y gates cancel out, two H gates cancel out. And then this one gives a C NOT gate, and two C NOTs will also cancel out. So that just happens the 5 gates I've implemented so far are all self-inverse. So if you have two of them, they cancel out. So that's kind of the first kind of simplification that we have in this QC Simplify website. And another example would be if you have an X gate followed by a Z gate, it turns out that X followed by Z is actually equivalent to a Y gate, but with a global phase. And if and global phase is just something that you can something that shows up in the math, but you can't actually measure it unless you were controlling the circuit inside of another bigger circuit. But X and Z are almost the same as Y up to this global phase. So if you have X and Z, it changes to a Y. And then again, if you put in a Y, that would cancel out. And similarly, if you have X, Z, and Y all next to each other, then that cancels out and gives us another global phase. And you can always reset things by clicking this trash can on the top right. So that's so there's a few simplification things here too. But the other neat feature that I've been implementing is visualizing how gates commute with each other. So for example, when I was taking my Intro to Quantum Computing course, there was some pretty cool things that happened that involved the Hadamard gate in particular. So if you have an X gate and a Hadamard gate, if you surround the X gate with Hadamards, then it turns into a Z gate. And that's kind of interesting, but why is it that it turns into a Z gate? So there's a few different ways that you could try to look into it, but one way is by learning the commutation rules. So if you have an X gate and you were to slide it across an H gate, it actually turns into a Z. So that's because an X followed by an H is equivalent to an H followed by a Z. These will do the same thing no matter which input or output you have, which is again why I don't actually have input and output. But sliding horizontally preserves the action of the circuit. So then you can see that if you had, for example, this XHX, that's actually equivalent to saying ZHH, and then H and H cancel each other out. So then that's another way to see why it would turn into a Z gate. And then there's also some pretty fun commutation things that happen with the C NOT. So the C NOT, it means that if this control bit here is 1, then apply a NOT to this bottom bit. So if this is 1, flip this bottom bit. So if you have an X gate and you wanted to slide it across a C NOT, well, that slides across no problem, because if we flip it before or flip it after, it's the same thing. But if you were to flip the top, because flipping it changes it if it was a 1 or a 0, that's going to change what the C NOT is doing. So you can't just slide it across. So what happens if you slide it across, you get an extra X at the bottom. And there's kind of a combinatorial explosion of all the possibilities you could try out. Like if you have a XZ over here, slide across, it turns into YY, and there's a whole bunch of different combinations that I've been playing around with. And you can also slide C NOTs across each other if you're sliding the same part. So yeah, so I've been working on this website so that you can kind of play around yourself to see how these commutation rules work, how this simplification works. And as far as I know, there isn't another tool that does it quite this way, where you can just slide things across, understand how you can manipulate circuits. So I'm hoping that this helps people learn how quantum gates work and how they interact with each other. So thanks for watching, and I'm happy to take any questions.
Thank you so much, Dante, for that amazing talk about your tools or what you want to. Anyone has any questions? If not, I have one question, Dante.
Mhm.
Well, what you could be work with another gates like rotation Y, rotation C?
Yeah, I might add some of those gates later on. But so far it does have these 5, but I might add rotation gates later.
Okay. And well, what happened? We trying to do well, maybe a possibility to build a Toffoli gate. We can build it certain similar. Well, we can reduce the number of the gates if found repetition gates. It's possible.
Using the Toffoli gate.
Yes.
Yeah, I might add that into. Yeah, when I added the C knot, it ended up being like a lot more work than I thought to get it to work properly. But because I have 2-qubit gates working now, maybe it'll be easier to get a 3-qubit gate to work as well. So I might add a Toffoli gate in the future too.
Awesome. Because well, you had a great proposal, and I think you can do it more. Well, you can work with this. Well, I think it's a great idea to improve the knowledge when we started in this area, because it's difficult try to see the resolution, the solution when we see a lot of gates. I think it's a great idea. Your work.
Yeah, I guess the tricky thing is every time I add in a new gate, then I'm kind of coding in the interactions with all of the other gates, and there's kind of a combinatorial explosion, especially with multi-qubit gates, because there's a lot of different things that you could, like, for example, making sure this worked properly was kind of tricky. And then if I put in a Y, then it doesn't even, okay, it doesn't, there's some commutations that it doesn't allow me to do because it would require me to add too many other gates, but this should work, for example. Yeah, so there's kind of yeah, every time we add a new gate, there's more and more combinations to put in. But I've been slowly adding new features to the website.
That's a good idea, actually. You had well, you had a lot of great exclamation for your work, and you had one question. Can you show the example where you slide an X gate across a
Ooh.
bunch of signals?
Yeah, I think that Elliot's talking about this, or if you have a whole bunch of C knots like this, then you can slide an X gate across and the whole thing is able to commute over, which is kind of a fun thing to code this particular feature. So there's a lot of combinations that you can do. I guess I could put a Z down here, and this would also work. So yeah, this is kind of what I mean about the combinatorial explosion. Just adding the C knots, I was trying to make sure that all of these situations would still work out.
Actually, that's awesome. Any other questions from this amazing platform? Well, thank you so much for your presentation and your time, Dante. It's really awesome.
No worries. I'll just, yeah, if you want to see it yourself, you can go in qcsimplify.com, which I put in the chat.